Okay, continuing our unit on probability, I want to talk to you in this lesson about unions and intersections primarily. We'll do so via Venn diagrams, two-way tables, a couple of other things, and looking at some examples. So, as you can see here, and obviously take the notes down while you go through this lesson. Consider the events A and B that involve numbers taken from the first 10 positive integers. So the first 10 positive integers, that represents the sample space. The sample space being all the possibilities. So the first 10 positive integers, 1 to 10, this is the set A, 1, 2, 3, 4, 5, 6, and the set B is 1, 3, 7, 8. Represent the two events A and B in a Venn diagram. So this is how the Venn diagram works. Nice way of displaying data or information where more than one sort of, set of numbers or objects is involved. So what we do here is if they belong to both sets, if there's a number that belongs to both sets, we put that in this little intersecting area here. So 1 belongs to both sets, 2 is just A, 3 belongs to both sets, 4 and 5 and 6 are just A, 7 and 8 are just B, and 9 and 10 we can slot outside because they're neither in A nor B, yet they are in the sample. So they're included in the sample space. So 9 and 10 sit outside, and that there now gives us our display of where our objects lie. Now the question then becomes, okay, let's start to look at sets of, and firstly the following. Let's look at the set that is A intersection B. Now I've just decoded that there. That's this little hump here means intersection, and so when you see that, that's what it's talking about. So what's the intersection of A and B? What's common to A and B? What numbers, what elements belong to both A and B? In this case, that's just 1 and 3. So the intersection is the intersecting elements are 1 and 3. A union B, this U, easy to remember because it is actually a U. A union B refers to events that belong to either A or B. So that's going to be all these elements here. So it's 1, 2, 3, 4, 5, 6, 7, and 8. A union B. So it's the collection of all the elements that belong in either set A or set B. Intersection belonging to both. Okay, let's move on and look at some probability questions to do with this Venn diagram. If a number from the first 10 positive integers is randomly selected, find the probability that the following events occur. An A occurs. So what we do is go in here and have a look at A. There are 1, 2, 3, 4 elements, 5, 6 elements that belong to set A out of a possible 10. So we would write down 6 over 10 here. A intersection B. Well, there's 2 in the A intersection B zone. 2 out of 10 is our probability of that happening. A union B, 1, 2, 3, 4, 5, 6, 7, 8 out of 10 is our probability that will happen. And a word here on mutually exclusive. Just have a look at this question. Are the events A and B mutually exclusive? Well, let's have a look at this definition here. A and B are mutually exclusive if their intersection is equal to the empty set or the null set. That's the symbol there for the empty set. So if there's no intersection, that means they're mutually exclusive if there are no elements that belong to both A and B. But in this case, are the events A and B mutually exclusive? Well, it's not an empty set, is it? We've got 1 and 3 sitting in there, so the answer to that is no. Okay, looking at another example now using Venn diagrams. From a class of 30 students, 12 enjoy cricket, 14 enjoy netball, and 6 enjoy both cricket and netball. Put this into a Venn diagram. Okay, well the way to go here is to go straight to the intersecting region. What goes in there? 6 enjoy both cricket and netball, so I'm putting a 6 in there. Okay, now let's work backwards. I've got 12 enjoying cricket. Well, I've got 6 already that also enjoy netball, so that's just 6 that enjoy cricket only. 6 plus 6 gives me that 12. And netball, I've got 14 that enjoy netball, but I've already got 6 here that also enjoy cricket, so that's just 8 that enjoy netball as well as cricket. So that's 14 total netball, 12 total cricket. Now I've got 30 students total. Let's add these numbers up. 6 and 6 is 12 and 8 is 20. That means we've got 10 students left, 10 students that enjoy neither cricket nor netball. So that would be the way to illustrate that information. Always start at the centre. So looking at some probabilities now to do with this situation. To find the probability that a person chosen at random will enjoy netball. Well, we've got 14 enjoying netball out of a total of 30. So that's just 14 over 30. But we should simplify that down to 7 over 15. In fact, there was one up here I should have simplified down. 8 over 10 should have been 4/5. Okay, so let's go back. Netball only, not cricket at all. 8 out of 30 there. 8 out of 30, which is equal to 4 out of 15. Both cricket and netball, that's the bit in the middle, isn't it? 6 out of 30, or 2 out of 10, or better, 1 out of 5. Okay, neither cricket nor netball, 10 out of 30, 1 out of 3. Okay, we're going to look at some two-way tables now. So we'll get a diagram drawn up and start talking about that. So let's talk our way through some two-way tables now. So we've got this information here in a Venn diagram. That's hopefully you understand now what this is about. This represents the number of elements in set A. There are 3, but one of them's in common with set B. There's 7 total in set B, 1 common with set A, 3 that fall outside that. Now we're going to transfer this into what's called a two-way table. It does the same sort of job as a Venn diagram, just a different way of looking at it. It's a different way of representing it. So if we go now to right, so what we've got here, this means A. So set A, set B. This little thing here, A dash, that means A complement, means not A. Right, so that means A. That's A complement. A complement or not A. Alright, so that's not A. Same down here for B complement, but not B. Okay, so let's go to what we've got here. Let's again work from the center. Always a good idea to work from the center out. So what this square here represents is A intersection B. So that's A intersection B. That just got a little 1 in there. So this, right, this here, this square here is A intersection B. Okay. Now over here, what else can we do? We got A intersection B complement. So what this is all this square represents the intersection of these two. So here A intersection B complement. So that's A intersection B complement. So that's not B. So let's get outside of B. Everything outside of B, boom, 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 boom. That's this 3 and this 2. But it's also got to be A. So that's just the 2 there. A intersection B complement. So the 2 goes in there. That's that. Let's just have a look at A and A complement. So that's outside A, not A, not A. Let's get outside A. So we've got it. There's a circle of A. So this 6 and this 3 is not A, but it's also got to be B because we're intersecting with B. So that's that 6 there. Okay, B complement, A complement is get outside A, but also get outside B. And that's just that 3 there. That's just what's left there. Okay, and then we've got some spaces here for the sum. So 1 plus 6, we put the sum in here. Do that in a different color. So that's a 7, 2 and 3 is 5. Okay, 7 and 5 is 12. 1 and 2 is 3. 6 and 3 is 9. So we should add across this row to 12, and this row should sum here down to, this is my sort of total cell there of 12. Okay, so that's my two-way table. It says the same stuff as that, just in a different sort of look. Okay, now to finish this little lesson off, just a couple of questions to do with the two-way table. Now this little n here, this says find the number of elements in this set. So that little n there means number of elements in set. In this case, A complement, so not A, intersection B. So that's that one there. So that is equal to 6. The number of elements in A union B. Right, now A union B. So this is all my A's here, 3, and this is all my B's here, 7. So that's 10. But remember, I've included the I've included that 1 twice. So that's actually 3 plus 7 minus 1, which is 9. Another way of looking at that is just to add up the 1 and the 6 and the 2. We leave out the A complement B complement intersection, because those three don't include A and B. So probably easier to see up here, isn't it? 2, 3, 9, A union B. So we can look at that as, we could say, well, that's the number of A plus the number in B minus the number in A intersection B. So the number in A, right, we've got that down as 3. Right, that's in that row, that column there, 3. The number in B is in that row there, 7. And the number in A intersection B is 1. So that's 3 and 7 is 10. Minus 1 is 9. Number of ways looking at that. 2, 1, 6 adds up to 9. 2, 1, 6 adds up to 9. Okay, last couple. Probability of A intersection B. So what's the probability of landing in that square there? It's 1 out of a total of 12, isn't it? 1 out of 12. So it's this one here out of a possible 12. So that's just 1/12. Probability of A complement. So not A. How many of those are there? There are 9 outside of A. Look at it here. Outside of A, 6 and 3. 9 out of 12. So that's equal to 9 out of 12, or 3/4. And finally, A intersection B complement. A intersection with B complement. It's that one there. It's 2/12, which is 1/6. If you want to have a look at that up here. A intersection B complement. So outside B. Everything outside B. That's these two. Then 2 out of 12. Okay. So they both they're easy. They have their sort of advantages. But it's good to know both ways of representing information in sets so that we can work out probabilities. It's a good way of sorting stuff out. So we're going to adjourn there, and we'll be doing exercise 8B when we next meet.